Section 2.6 said, uh-oh, now we have these things called rational functions, and they have their own stuff going on. So yesterday we reviewed how rational functions have domain problems. And where are the domain problems in rational functions, guys? Because the denominator, what's Jason saying? Denominator can't equal. So discontinuities happen on the bottom. Two different types, wholes and vertical asymptotes. Wholes are removable, meaning you can factor in. I know what she's mean, and I like the slash, but reduce. Good. You can factor and you can reduce. Those are wholes. Vertical asymptotes, you're stuck with. There's this whole trick, 0 over 0, number over 0. Whole vertical asymptotes. Then we said, hey, remember there are these things called horizontal asymptotes, and there are degree tests. So that's what you were practicing right now. Number 1, what do you guys think? Either individually or hopefully all together as a group, you guys hopefully came to a consensus. Number 1, top wins, bottom wins, tie. I agree. We'll get back to the answer in just 1 second, but I agree. Top wins. Why? But he has a 33. Doesn't matter. The power. X squared is stronger than x to the 1, regardless of the coefficient. How about number 2? Who won? What was the degree of the top? Exactly. X to the 0, because anything to the 0 power is. X is to the 0 power. Bottom wins. How about the last one? So let's see. Oh, hey, it was right in order. Anyway, unintentional, maybe, not really. But coming back. So what are the answers? As soon as you see top wins, if some of you want to understand why, we could do long division, and when we divide, it would be nasty, but we would get a polynomial out. When we divide the top by the bottom, we'd actually get a linear function, a polynomial out. And polynomials go to infinities, whether it's this way or this way or this way or this way or this way. Polynomials go to infinities. They're not bound to a horizontal asymptote. So whenever the top wins, there will never be a horizontal asymptote. None. None. Now, there could be something called an oblique asymptote. That's what we talked about at the very end of yesterday. We'll get back to that in a second. If the top wins, long division gets us. Sometimes there's an oblique asymptote. We'll get back to that in a second. But no horizontal asymptote. Okay. If the bottom wins, if it helps, bottom is the divisor. That's what we call him. He's being divided into the top. If we tried to do long division, we couldn't do anything. This is not an improper fraction like that one. We can't really divide in and get out a polynomial. But what you can think, what if I gave you one pizza, a big one, okay? And then I told you to divide it in 2. Okay, pretty good piece, right? One piece, half, half. Pretty good piece. Thanks for the 2 head nods. Go team. What we're doing is we're going, or x is going to infinity and to negative infinity. If you guys look at your notes, x is going to infinity, negative infinity. I know it's hidden here. And we're asking ourselves, what's y doing? So the division gets bigger and bigger and bigger in positive ways and in negative ways. So let's divide it more and more and more. So let's say we divide the halves in halves. So we divide it in fourths. What happened to your piece? Just got smaller. What if we divide the fourths into halves? So we divide it into eighths. Smaller. How about 16ths? How about 32nds? X is going to infinity. The bottom is going to grow faster than the top. So it's going to be dividing, 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 dividing. What's happening to your pieces? Going, as we keep on going to infinity, what's going to happen to your piece? It's going to get so small it's not there. If you could realistically actually keep dividing, which we know eventually. You're like, well, sorry, that's all we got, right? What's my horizontal asymptote? Whenever the bottom wins, you're going to divide, 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 going to 0. You're never going to actually get there, mathematically speaking, as you go, as x goes to infinity or negative infinity, but you're getting closer and closer and closer and closer and closer. There's a thing called Zeno's paradox, but we'll talk about that some other day. How about number 3? There's a tie. The top doesn't win, so the polynomial doesn't win. You're not going to infinities. The bottom doesn't win, so you're not going to 0. But you're still being held in check. You're not going to 0. Way. Is there going to be a horizontal asymptote? And the answer is yes. So what's the deal with the ratio of the leading coefficients? Oh, they're in front, 7/2. The leading coefficients are the coefficients of the degree terms. What are the leading degree terms? These guys. We look at the ones where the degrees are, where the highest exponent of x is. And then we take the ratio of those leading coefficients. Technically, there's something, a trick for really, really, really hard expressions that aren't just polynomials over polynomials, where this number is always right, the ratio is always right, but sometimes the sign, positive, negative, can change. So if we keep going, if you keep going, harder functions like in calculus one day, we might have to do some, check the sign, but not now. Our functions are nice and easy. Little polynomial top, little polynomial bottom. No big deal. But who's this guy called oblique asymptote? And why did I bring him up with number 1 over here? Who's this guy called an oblique asymptote? And why did I bring him up? Can you guys graph this function in your graphing calculator real fast? 5 minus x squared all over 33x. I'm going to get my calculator out too. Just graph him. Just graph him. We know what these horizontal asymptotes, okay, it's a little dashed line. It gets closer, 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 closer. We had some graphs up on the board yesterday with horizontal asymptotes. But who's this oblique guy? He's not horizontal. Supposedly, he's still an asymptote. According to our notes, this function has a slanty or an oblique asymptote because the top's degree is 1 higher than the bottom. That's the reason I pointed him out. The squared is directly or exactly 1 degree higher than the linear down below. So if we divide, we would get a line out. A line? As you guys are graphing, hopefully you're using that cool fraction-y trick, alpha y equals. On top, putting the 5 minus x squared. On bottom, putting the 33x. Your window might need a little bit of help. Does Zoom Standard work, guys? Oof, it's kind of hard to see. It's because of the 33. What if I try, how can I make this easier? We could try Zoom Fit. I'm not sure if that's going to be nice though. Oh, it's a little bit better. This is weird. What's this function doing? It's kind of like it's slanting on the edges. Do you guys see it? It's kind of like it's swooping in towards something. I wonder what it's swooping in towards. Oblique asymptotes. Yesterday, what was our hint about how we find them? Whenever the top's degree is 1 higher than the bottom's degree, the squared is 1 higher than the linear. Use long division. So what would happen if we tried to use long division with this guy? Plugging 5 minus, well, we don't write it like that. We write the highest degree term first, even if we don't like them. Write the other guy out here. Oh, why is there a 33? Well, how do we make it match? You guys might not like it, but does that make it match? Yeah, the 33s will reduce. The negative x times x is negative x squared. Oh, whew, we don't even have to distribute. That's good. So then, when I bring it down, I just end up with a 5, and that's my remainder. Wait a minute, what did I tell you yesterday about remainders with these guys? Yeah, ignore the remainder when you're trying to find the oblique asymptote. Can you guys graph the line y equals negative 1 over 33x? And see if that has any special meaning in that graph? Graph the line, negative 1 over 33x. After this function, keep him, negative 1 over 33x. My calculator knows PEMDAS, so when I write it like this, it says divide, but just those two. then multiply. So it knows PEMDAS, divide and then multiply. If you wanted to divide by x2, you'd have to put parentheses, just in case you're wondering. But what's special about that line? Oh, there's the oblique asymptote. Make it dotted and you've got it. When we graph functions with oblique asymptotes, we're not going to make horizontal lines. We're going to make slanted lines at the actual location of the oblique asymptote. And then our function is going to need to skim that slanted line instead. Does that kind of make sense? So oblique asymptotes, it's just an actual line, but you have to make that line that comes out of the division. You have to make him dotted. And when you make him dotted, then you'll go ahead and have what my curves are supposed to approach. So horizontal asymptotes, nice horizontal lines that the curves are going to approach, found by the bottom winning, horizontal asymptote at 0, or a tie happening, horizontal asymptote at the ratio of leading coefficients. If the top wins, there is no horizontal asymptote. It's not going to be getting closer and closer to any horizontal line, but it may have an oblique asymptote. But that's only going to happen when division gets you a line out, ignoring the remainder. And that's only going to happen when the top is 1 higher than the bottom. And with that, we've covered all the asymptotes. The vertical ones, the horizontal ones, the degree tests, and then the oblique ones, the long division, only when a line is left over. So what else was there in section 2.6 when you guys were doing homework last night? I don't think I made you get all the way through. Let's go ahead and peek real fast. I do have the answers up, but you guys, most of you didn't get to finish all of the answers, right? Let me pull up the book really quickly, and I want you guys to let me know where you got stuck and or where you stopped. I don't necessarily want to know where you stopped. If you just decided to be like, haha, she said halfway I can stop, even though you could keep going. I don't want to hear that, but what I do want to hear is where it got hard. Is that okay? So not like I don't want to call you lazy, because I did say you could only go halfway. So not the laziness factor, not the, it's good enough factor, but instead the, no, it actually got hard here. Sorry, it's taking just a couple seconds to search through the 1,091 pages. It's coming. There we go. All right, where did it get hard? 60 or 16?
45.
Salma 16, right? 16 was, oh, 60. Oh, okay, good. I was like, it's kind of rough. Okay, 45. Let's start there. Those were all, wait a minute. How could you guys have figured this one out? But here's what's tricky. Didn't 2 of them have, I mean, these ones had totally different vertical asymptotes. So hopefully these ones were easy. This one, -5. Oh, look, there's a 5. Anyway, but how do you know the difference between these 2? They were both at 2. Yeah, yesterday, didn't we talk about how if there's no squared, it'll be up and down? If there's a squared, they're both up. Anyway, sorry, number 45. Too many hints. Okay. What was going on in 45? Lots of directions, I get that. But what were they asking? Okay, graph F, graph G, after figuring out the domains. That's okay. Yeah, there's a lot of directions. So, question, what's this guy's domain? No, actually this guy, why is it all real numbers? Yeah, there's no denominator. So this guy is all real numbers. This guy says, no, x can't equal -1. But wait a minute, why are they so stinking similar when you graph them? What happens when you factor and reduce this guy? Oh, this guy is that guy. The only difference is that there's a hole at -1. And does the graphing calculator show you like a ding, 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 whoosh, there's a hole? No. It's just going to graph right over it because the pixels basically aren't small enough to show you a hole that's infinitesimally small. and it takes up no space whatsoever until you put 2 points together. Anyway, that's going into like first dimension, second dimension craziness. Actually, 0th dimension to first dimension. But anyway, long story short, your graphing calculator doesn't show you a hole. Mr. Crawford, if you guys remember him, he used to have a way to make it show you the hole, but even then you had to be in a certain zoom. It was complicated. It's better for us just to say, we know x can't be -1. So if you were to graph the two, mx plus b, the intercept is -1, 0, -1. The slope is up 1 over 1. No big deal, but when you go down to -1, f says, no, 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 keep going. G says, nope, pass straight through. So they're the exact same thing, just he has a hole, whereas he says, nope, I'm fine. Which is why when we reduce, what do we have to say so that they're not actually incorrect? We can't just say him. They're not the same. But if we say, yeah, if we say x can't equal -1, it's totally legal. And it's a whole lot easier to deal with x minus 1 than that whole nastiness at the beginning. But then Salma also said number 60 got weird. Ooh. Thanks, Salma. That's exactly the kind of problem I was looking for. What's going on in this section of directions, guys? Domain, intercepts, vertical slant asymptotes. I would also say horizontal asymptotes. Additional solution points. Oh no. What does this sound like? Sufficient solution points. You guys remember that direction in section 2.5? What were we supposed so big. What were we supposed to be doing? We were making a table in order to sketch a... We're supposed to graph these things by hand? Don't worry, I got you. Let's go back to our notes for a second and say, how do we put it all together to make a sketch? I got you. Salma, thanks for that question, kid. This is how. This is how to do those problems. This is how to take any fraction and say, I don't need a calculator. As long as it's not too hard. Okay, I'm going to put everything together. Not everything from the whole chapter, because we were doing polynomials for a long time. But in some ways, there's a polynomial top and a polynomial bottom, so maybe I kind of am putting together the whole chapter. Oh, not imaginary numbers, because we're not going to sketch imaginary things. Okay, that's the one thing I'm going into. Try to simplify. What do I mean? I mean, let's do green. This is all review. Try to simplify. Factor and reduce out the holes. Simplify. Factor and reduce out the holes. And as you do, state your domain. Set that denominator equal to 0. Find the zeros. Because careful, if you factor and reduce and you don't state your domain, you're going to be a little bit off. Because if you factor and reduce, that should have been a hole, and you can't forget that when you go to graph. So factor and reduce out the holes, state your domain at the exact same time. What are your discontinuities? What is x not allowed to be? Find and plot the y-intercept. Set x equal to 0, right? You're going to find whatever. It could be 1b. It could be multiple intercepts. No. Actually, it can't be. If it hit the y-axis twice, it wouldn't be a function. So maybe it will only 1 or none. Find, plot the x-intercept. Set y equal to 0. We've already used b, so let me use a instead. Now, this is where you can have multiple ones, right? These are the zeros of the function. And you've already factored, so we're okay. You've already factored, so we're ready to find the zeros. That's okay. Find and sketch the vertical asymptotes. The nice thing is you should already know who they are from the domain restriction. So quick reminder, they were the non-removable denominators. They were the non-removable zeros of the factors. They were the ones that are left after you reduce. Horizontal asymptotes, degree test. Top directions pi. Do we have any horizontal asymptotes to add to our sketch? Now, the struggle is I put horizontal, the directions put slant, and we're both wrong because it should be both. So I'm going to go ahead and put in horizontal asymptotes, and I know it's really messy, I'm sorry, and oblique asymptotes. Degree tests and then oblique asymptotes, that's the long division. But remember, oblique asymptotes at the top win. When the top wins, but only by 1. Sorry, my 1 does not, but the 1 doesn't. Only by. When the top wins by just 1 degree. Find plot test points. Oh, hey, it's just like what we did last time with the table. Yeah. What did we call that table? Do you guys remember? Yeah. I think you almost had it. Sign chart. The table with the intervals and the test points. And then connect everything that you think should connect. I mean, don't go connecting over a vertical asymptote. We're in big trouble. Don't go connecting over a horizontal asymptote. We're in big trouble. But use smooth curves to connect what you have. Let me give you a second to remind yourselves of any other of this stuff that you need to write down. And then I have an example, and hopefully it's going to totally help you guys with what's to come as you try to finish up homework tonight, section 2.6. You guys are going to be in your PSAT tomorrow, so we're not going to have class tomorrow, like we already talked about. Which is why on Thursday both the rest of 2.6 and 2.7 are due. Because 2.7, to be honest, I have to show you a couple tricks. But long story short, if you get down the couple new things and you remember in this example how to do a sign chart, you're golden. You're solid, you're ready to go on 2.7. It's a quick section. So tonight you can finish up 2.6. Tomorrow night, I should say, work on 2.7. That's how I would split it up anyway. A lot of you guys already have these clues written down, so I'm going to go ahead and dual page it. Let's go to an example. And let me show you how I would tackle a problem like this. Now, granted, my steps are just a little bit different, so let me add in what the book says. It doesn't say to factor, but you kind of got to do that. The book says, A, find the domain. Find the domain. You're going to have to factor first. And I'm going to say factor and reduce. Sign chart, that's when the book says, you guys just read it a second ago, that whole weird plot additional solution points. In other directions, it says possible or reasonable solution points. That's that whole extra piece. And I'm adding in horizontal asymptotes because they really, 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 really help. The book doesn't say to do it, but I say to do it. I have them all now? Factor to get the domain. Intercepts, y-intercepts, x-intercepts. Vertical asymptotes, I add in horizontal, oblique. Okay, so if you do all of this, you're meeting A, B, C, D, E, F, however many they had. Directions, okay? So factor, what do we got? Who is this guy? Numerator. You guys agree with Matthew? X minus 2, x plus 2? I think I agree too. I'm going to put a little y equals just to help my brain a little bit. So x minus 2 over x plus 2. Factoring the denominator. Jason, what are the factors of the denominator? Yeah. Yeah, that makes sense, right? So then x minus 1, x minus 2. Wyatt, what's going to reduce? Wow. Why did I just go to honors? I'm so sorry. I just went to honors real quick. Chris, what's going to reduce? he stole it from you. Yeah, Chris Smith. The x minus 2. Good. So what's remaining is the x plus 2 all over x minus 1. But careful, my domain restriction. Chris, we're still on you. When you take away the x minus 2, what do we have to say x wasn't or isn't allowed to equal? Close. That's. But since he's still there, I'm not going to actually state him yet. I'm going to state who just disappeared instead. Does that make sense? Yeah, so 2. Good. So when I take away the x minus 2, my life is so much easier kind of for the rest of the problem, but I can't forget whole. I can't forget my whole. So what is my domain? Okay, Chris Massey, what's my domain? Good. Can't equal 2, but also technically, let's look at the whole thing. What else can't it equal? Good. So my domain, x can't be 1 or 2. But if you want to label it, my vertical asymptote is the one that's left, right, guys? My vertical asymptote is at 2. No. Who's the one that's left? Yeah. My vertical asymptote is the non-removable one. So my vertical asymptote is at 1. Technically, what's going on at 2? Here I can say there's going to be a hole at, because x isn't allowed to equal. I'm just going to take a volunteer on this one. What's my y value of my hole? How could I figure that out? If I plug it in here, I'm going to get 0 over 0. If I plug it in here, I'm going to get 0 over 0. Where do I want to plug it in? Yeah. 2 plus 2 is 4 over 1. I can figure out where the hole is by plugging it into the very last reduced form. Okay. Whew. I factored, found my domain, figured out the hole in the vertical asymptote. I'm well on my way. Technically, we can go ahead and maybe you guys realize I'm just going to be using those clues. Maybe we can just start building our graph. So far, I have, let's see, 1 and 2 are my only important values right now. Okay, so far all I know is I have a hole at 2, 4, and I have a vertical asymptote at 1. Well, that's exciting. I need a little bit more than that. So, y-intercept. You guys have your notes right there, right? Who do I set equal to 0? So y equals, let's set, now we could go here, we could go here, but I'm going to go ahead and for the rest of the problem use this guy because he's a whole lot easier. I already have my hole marked, I'm good. Let's just use the easier reduced form. So plugging in 0, what's 0 plus 2 over 0 minus 1? Negative 2. I think my y-intercept is going to be when x is 0. Y is negative 2. I can put that in, and that's an actual point, not a hole. Got him. Okay, x-intercept. Who do I set equal to 0? Oh, the y instead, huh? Whenever there's division, what do we need to do? Yeah, let's multiply to the other side. If you guys realize, multiplying by x minus 1, we get 0 again. Which leads us to x plus 2 equaling 0, aka x equaling negative 2. Oh, there he is. X is negative 2 and y is 0. So far I have my domain, I figured out my hole, I have these special points. There we go. We already know my vertical asymptote, we already graphed him. Horizontal asymptote, degree tests. Top wins, bottom wins, tie. So what is the ratio of the leading coefficients? All right, man, what's the ratio of the leading coefficients? That's okay. Harana, what's the ratio of the leading coefficients? Yeah. Who'd you look at? Or which pieces did you look at to find that? Good. The highest ones, right? Good. So x squared over x squared, 1 over 1 is 1. Oh, sweet. Let's come over here and let's do the dotted line at 1. Okay, we're getting there. Some of you might actually be able to guess right now and probably get a pretty good picture. Is there an oblique asymptote? Why not? I totally agree. Same power. And to have an oblique asymptote, the top needs to win by, so none. Forget that guy. Sign chart. What did I write down in the sign chart category? Make a table using what values? Yeah, the special x's. And I think I even put it in our notes. What special x's did I say to use? I think I wrote it. Did I not? There's too much silence. Set up a sign chart between x-intercepts and the vertical asymptotes. So I even give you a hint as to which x's to use. I give you a hint as to which x's to use. So what do I have? I have 1, I have 2 as my domain problems, and I have the intercept of -2. So I'm going to go from -infinity to -2. I'm going to go from -2 to 1. I'm going to go from 1 to 2. Oops. And from 2 to infinity. I'm breaking down my x-axis into all the important x values. So there's this interval to this point, this interval to this point, this interval, and then that interval. Did I get them all? So I have 1, 2, 3. Oh, that guy. There we go. And then 4. So I'm giving you guys a system because they just say, I don't know, pick points. I'm saying, no. Pick points strategically. So let's pick a point. What's any x in between -infinity to -2? Any x on this side of the graph? In between. Yeah, that's an easy one. Now, we have -1 and 0. Which one sounds nicer to plug in? Wait, we already know that one. We plugged in 0. -2. Oh, sweet. Haha, we just get to use our intercept for that. What's in between 1 and 2? Yeah, 1/2. And then in between 2 and infinity? Ooh. 1/2 is in between 0 and 1, huh? So 3/2 or 1.5. And then 3. Now guys, I already told you I like this form a whole lot better. So much easier. So I'm just going to plug in really fast. -3 plus 2 is -1. Over -3 minus 1 is -4. That's going to go ahead and be a positive 1/4. A point that I can plot. It's not very high, but there he is. 0, -2 is already graphed. 3/2. Ugh. 3/2 plus 2. I would do 3/2 plus 2 is 4/2, which is 7/2. I'm making a little common denominator stuff going on there. Over 3/2 minus 2/2 would be 1/2. 7/2 times the reciprocal of 1/2, which would just be 7. Turned out a whole lot nicer than I thought it was going to be. And then 3 plus 2 is 5, and 5/2 is my last point. I'm going to go ahead and graph those real quick, just so we have them. 3/2, 1.5, 7, that's like way up here somewhere. 3, is that 5/2 or 2.5? Do you guys think you might be able to sketch knowing the horizontal asymptote? Knowing the vertical asymptotes? Knowing the discontinuities? And knowing that's what we're supposed to connect with a smooth curve? Now there is one way that we could double check that we're right. We could double check that our behavior, this was the one other thing that we talked about this section, near the vertical asymptote makes sense. And we could test something like what's going on at f of 0.9 and what's going on at f of 1.1 to make sure that going negative and going positive makes sense. We could do that if you wanted. If you're a little paranoid, not quite sure you got it right. And if we plugged in 0.9 and plugged in 0.9, you would realize that would be a negative. So going to -infinity makes sense. And if you plugged in 1.1, you would realize going to positive infinity makes sense. It just backs up what my graph already showed. Dun, 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 dun. Done sketch. Does that make sense? Did all the clues add up to get exactly what we needed? Yeah. So what did we do? Quick recap. We factored. We simplified. We thought about intercepts, put in important points, got a sign chart, and we're able to finish from there. Okay, here's a dealio. We're kind of stuck between the rock and a hard place just a little bit. We're kind of stuck between a rock and a hard place just a little bit. And let me show you why. We have retreat next week. And it would make everyone's life just a little bit better if we could get through section 2.7 before Thursday. Now, what's the problem with you guys tomorrow? You have the PSAT. So here's what I'm thinking of doing. I'm showing you today, right now, the general gist of what's going on in section 2.7 and why I think we'll be able to do it. There are some notes that will be important to cover, and I'm actually going to go ahead and give whoever's here tomorrow, the seniors, the upperclassmen, give them a chance to take the notes. I'm going to take a little baby video. It's not going to take long. I'm going to actually show you how to solve an example instead of having you take notes today for the last couple minutes of class. Okay? I'll let you take a picture of the notes actually before you leave, so you don't even have to look at the video. But I'm going to show you an example of how to do 2.7 to see if that'll be enough with the notes that you write down to tackle this homework. There's only one on the test. I think there's two. There's one multiple choice and one long answer. There's something called key numbers in section 2.7. If you want, you can go to the back of your homework spirals. You can put it there if you want to do the example with me. There's something called key numbers that you guys are going to write down in your notes. If you want to have your phone out, don't be like snapping or anything. You can have it out to take a picture in just a second of the 2 pages we just skipped to write into your notes tonight, tomorrow. There's something called key numbers. And for polynomials, those key numbers are just the zeros. How do we find the zeros of a, to find the key numbers, we would just take the x squared minus x minus 6. Now here's the problem. To find zeros, we have to get one side equal to 0. So if it's not, we would first get one side equal to 0. But then we do exactly what it says if it was an equals, and we would factor to get x minus 3 times x plus 2. And we would end up with our zeros, or our key numbers, at x equals negative 2 and 3. As you guys write down notes, the struggle is there's this inequality, and the inequality is easy with lines. It's hard with any polynomials or rational functions. And so the nice thing is, something that you guys already learned and we just practiced is going to be the key to solving. You're going to make a sign chart with intervals marked by the key numbers. You're going to do test x's. And the only difference is instead of plugging in to get y's, which you're going to do, you're going to ask yourself the question, true or false? Kind of, possible, not possible, true or false. You're going to go all the way back to the original. You're going to look at, if I were to plug in for x minus 3 and x plus 2 less than 0, you're going to ask yourself, is it true or is it false when I plug in the test numbers? So what I would do is I would have taken these special key numbers, done an interval from negative infinity to negative 2, from negative 2 to 3, and from 3 to infinity. I would pick, just like we did with graphing, any numbers that seem nice to us, like maybe negative 3 and maybe 0 and maybe 4, just something in between. I'm going to come up here and plug in and say, okay, if I plug in negative 3 minus 3, that's negative 6. If I plug in negative 3 plus 2, that's negative 1. You just have to ask yourself the question, is 6 less than 0 true or false? If it's false, guess what? That interval is not in the answer. If you keep on plugging in, you would eventually, and I just know what's going to happen already, you would keep on plugging in and testing. You would find however many true intervals there are, and guess what the final answer is, guys? All x's within that interval is the solution. Let me go ahead, and if you want a picture of this page, go ahead. I'm going to show the notes that I want you to take down. That's all of section 2.7. Rational numbers just get a little bit harder. Let me dual page it. Grab a picture on your way out. And that's for tomorrow night's homework. I will do an example of a rational function and record it real quick at the beginning of class tomorrow. So you might want to check that out to help you on homework tomorrow night. Sound good? Okay. Thursday's a big old day, a big old review day. And I'll cover any questions, all questions you guys have, okay? Good job, guys.